We'll start the miscellaneous ones. A bunch of everything. You will see, it's like a multiple choice and in long answer. The AP likes this style of question where they give you a chart and it just opens up all sorts of questions they can ask. They can like, from this chart, I could ask a sneaky intermediate value theorem, mean value theorem, left Riemann sum. Like, there's so many things they can ask you if they give you a chart. So they're a great one to start and think about. Okay, a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differential function f. So it's nice to know that f is a rate measured in gallons per second. And t is measured in seconds since pumping began. Selected values of f of t are given in this table. Using correct units, interpret the meaning of the integral from 60 to 135 f of t dt in the context of the problem. Okay? So you have to make sure that you're using gas and gallons and talk about the context of the problem when you write your answer. You can't just say, this is a definite integral going from 60 to 135 of the function f. That's saying what the symbols mean, but not in the context of the problem. Oh, look, it has right Riemann sums. Use right Riemann sums with 3 subintervals to approximate the value. All right, so first of all, what does this represent? It's the total number of gallons of gasoline pumped into the gas tank from time equals 60 seconds to time equals 135 seconds. It's the accumulation of change of gallons from that time, from 60 to 135. Now, since we don't have the function and just the values, to figure out how much that would be, if we use right Riemann sums, we're going to look at the distance in between these, 30, 30, 30, 15, 15. Right? But we're only looking from this part, from 60 to 135. So our subintervals are going to be 30, 30, and 15. That matches up with them saying use the 3 subintervals. And we're using the right values for each of those. So if I look back at my chart, in the first subinterval, this is the right value. In the second subinterval, this is the right value. In the third subinterval, that's the right value. So that would make our right-hand sums. Okay. Question? Or you have to specify what interval.
No, the text that you put in a little up that one.
This one here?
Yeah.
You have to say the context of gasoline, right? From time equals 60 to time equals 135.
Do I have to like mention what does it mean?
Yes. Yeah. Because it says, because it wants in the context of the problem.
Oh yeah, I see that.
Yeah. Yes.
Why is it 30 times 0.85? Let's say one on the table of values.
Oh, that is a good question. Because it should be 1. I circled the 1. I'm not sure why it said 0.85. That's just a typo. Is it 0.1?
Yeah.
0.1. Yeah, there's no 0.85 anywhere. Thank you for noticing. Either this number is still right, and it was just a lapse in thinking when I wrote the 0.85, or the number is also partially wrong, but we're not going to worry about it. Must there exist a value between 60 and 120 where f prime of c equals 0? So now this is going to lead you down through either mean value theorem, extreme value theorem, or intermediate value theorem. And sometimes you might think the wrong one initially. When we were working on one before, we went down, we tried mean value theorem and realized it wasn't mean value theorem afterwards. Okay? Right? This is an important concept. The question, okay, says right here, differentiable function. If it tells you differentiable, you know for sure it's continuous. If it tells you continuous, it does not mean differentiable, right? Differentiable will always imply continuous. Continuous doesn't, like I can draw something continuous with a sharp point, not differentiable, okay? So if you get differentiable, it's continuous. Sometimes they'll say twice differentiable, then you know that the original function's continuous and the derivative's continuous. And they like to say that language. So here we've got f is differentiable, that means f is continuous. If we look at the secant line, from 120 to 60, the secant line has a slope of 0. This is the derivative of our rate, so it would be gallons per second per second. If the secant line is equal to 0, by the mean value theorem, there must exist a point C for which f prime of C equals 0. The mean value theorem is the only one that needs continuous and differentiable. Intermediate value theorem just needs continuous. Extreme value theorem just needs continuous. Question? Yeah, and Rolle's theorem is just a specific example of the mean value theorem. So you could say, by Rolle's theorem, there must exist, and that would be perfectly fine as well. All right, part C. The rate of flow of gasoline in gallons per second can also be modeled by g of t for 0 to 150. Using this model, find the average rate of flow of gasoline over the time interval from 0 to 50. Average rate of flow of gasoline, and this function is a rate of flow of gasoline. So it's important to note what function we have when figuring out averages. Okay. Because we want to find the average of this function, we want to use the average of a function where you do 1 over the disk of 150 minus 0 is 150, and then the integral from 0 to 50, and get the value. The secant line of a function is the average rate of change of the function, right? So if I had a displacement function going to kinematics, if I found the secant line of my displacement, that would give me my average velocity. But anytime you want to find the average of the function you have the equation of, right? If you wanted to find if you had your displacement and said, what's the average displacement, then you need to use this integral formula. Again, they can sometimes be easy to mix up. And using the model G, defined in part C, find the value of G prime of 140 and interpret the meaning in the context of the problem. So here's G. It's a calculator question, so do not waste a lot of time doing anything other than using your calculator to plug it in. Maybe you had already typed this into Y1, and you could use your derivative button on your calculator, or maybe you just do that derivative button on your calculator and type in that whole function. Just a reminder, so that derivative button is under math, number 8. So I could do d dx, and I could write that whole equation in. Of course, it has t's, but we would use x instead. But if you had, just like we did last time, already written it into y1, then don't retype it. Use the y1 instead. And then in this case, we wanted to find it at 140. So then after you typed in the whole equation, this is where you would put 140 in. And you would get the answer very quick. So again, knowing the tricks of your calculator, very nice. Now, interpreting the meaning in the context of the question. The rate at which gasoline is flowing into the tank is decreasing at a rate of 0.005 gallons per second, right? Because our first one was g of x was gallons per second. This is the derivative, so it's gallons per second at a time t equals 140. I think this is why they don't get me to write exams. I think I would create some silly question where you have some multiple derivative and the original function is in gallons per second, and then you have to interpret it in the context of the meaning. What is the derivative? So then you would have to write gallons per second. This is why they don't let me write exams. We have time for one more miscellaneous question. Take a brief look at questions 2, 3, and 4. And I guess if I were you, I'd pick the one that looks the scariest to me. They're like 2 and 4 involve graphs, and you're going to have to do areas under those graphs. Very, very typical questions. Whichever ones we don't show, I'll put the answers on the video as well, so you can see those after. 3 is another chart one, which we did a chart one here, but it's a little bit different. What are you feeling? 2, 3, or 4? 3, 2, 3, 3, 3, 3. Okay, I'll show you 2. I'll just put the answers for 2 up for those of you that are sequential. That way it's going in order. You can pause this. Afterwards. I just zoomed in so that it's a little bit easier to read. All right, and we'll go then to example 3, another chart. Ooh, and it's got f of x, f prime of x, g prime of x. The functions f and g are twice differentiable. So that means f is continuous, g is continuous, f prime is continuous, g prime is continuous. We've got their first and second derivatives. And then h is the composition of f of g of x. Find h prime of 7 and show your work. So first of all, since g of x is inside of f of x, if I wanted to find the derivative of h of x, it would be a chain rule, where you do the derivative of the outside function, keep the inside function the same, then multiply by the derivative of the inside function. So h prime of x would be f prime of g of x times by g prime of x. Then h prime of 7 would be plugging in a 7 for all of those x's. And then we go to our chart and hope every number is there. Well, g of 7 is there, it's 0. G prime of 7 is there, it's 8. So I'm going to have f prime of 0 and g prime of 7 is 8. And f prime of 0 is there. That's 3 halves. And so we get 12 in the end. Okay, what's the key here? Knowing how to use the chain rule like with abstract functions. So what always happens in the chain rule is you do the derivative of your outside function, that's your f, and you keep your inside the same. Then afterwards you multiply by the derivative of that inside function. K is also a differentiable function, which tells us that k is continuous. K prime of x equals f of x squared times g of x. Is the graph of k concave up or concave down at the point where x equals 4? Give a reason for your answer. This is not where you say, I have no idea, I went concave up because it was a 50-50% chance. That's not going to go over too well. Well, how do we find out if something is concave up or concave down? We're going to have to look at the second derivatives. How do we do the second derivative? Do you see that this is a product rule and a chain rule? So, how does a product rule work? Keep the first function the same, multiply by the derivative of the second, then keep the second the same, multiply by the derivative of the first, and the derivative of the first has a chain rule. We take the 2 out in front, keep the inside the same, then multiply by the derivative of the inside function. Then when you plug in 4, wow, we get to have a lot of fun with our chart. But all of those values are on your chart, and you get negative 40. And after all that, if you say concave up, we're in trouble. So because it's negative, it has to be concave down. No. In fact, I don't know if we can say that k double prime is continuous. I think we can say that k is continuous, and I think that might be a typo in this answer. Right? Because if k is differentiable, then k is continuous. But I can think of functions that are differentiable, and I can get down to k double prime and have a problem. Part C. Let m be another function defined by m of x equals 5x cubed plus 0 to x of f prime t dt. At this point, have you seen the fundamental theorem of calculus part 1 so many times that when you see this, you're like, oh, I know what's coming. Something to do with the derivative is definitely coming up. But it says, find m of 2 and show the work that leads to your answer. So m of 2 would just be plugging in values. Okay? Plug in 2 for x here. Now how do we interpret 0 to 2 of f prime of t dt? So this is going to use the fundamental theorem of calculus part 2. You know that the antiderivative of f prime will be just f. And so we just need to figure out, this will be 40, what is f of 2 minus f of 0. Once again, those values are on your chart, and we get 37. And is this function m increasing, decreasing, or neither at x equals 2? Justify your answer. Well, how do you find out if a function is increasing or decreasing? You find its derivative, and you plug the number into your derivative. So what we predicted is going to happen right now. We're going to find our derivative. This is going to just be 15x squared. But the derivative of 0 to x f prime of t dt, that's the fundamental theorem of calculus part 1. That's just going to be f prime of x. Then at 2, we're plugging things in. F prime of 2 was given to be negative 8 from your chart. And you get 52. And because it's positive, we know that it's increasing. One thing that they showed on the videos, like the Mark and Verge videos, is that sometimes they might put a question like this on the calculator section, even though you get really no advantage. Usually on the long answer, not so much. But sometimes on the multiple choice, you could get some multiple choice on the calculator section where you're like, I actually didn't need my calculator for that. So. And I'll show you the answers for the last one. Here, I'll just wait. So that you have them as well. Everybody done on this one? So I'll show you number 4. So if you want to try it on your own, you can come back and look at the answers. There's part A. There's part B. And finally, C and D. A lot of people use this wording, candidate's test. Or an extreme value theorem, when you check every possible point, they call it the candidate's test because every possible point is a candidate to be the winner of the maximum of the year or the minimum of the year. I just always called it use all the values. And then I was at a conference once and they said, oh, you just used the candidates test. And I was like, what's that?